Okay, so in this third electron configuration video, what we want to talk about now are the ions. So bismuth, going back up to this example that we looked at the end of the second video, we saw that it had an s2p3 valence. We know bismuth is a metal because when we look at it on the periodic table, right, we've got our metalloid stair step. It's to the left of that, so it's a metal. It means it loses electrons, and it's a type 2 cation. And what we know about bismuth is that it's either a +3 or a +5 as a cation. So if you have a positive cation, electrons are removed from the valence electron shell first. So if bismuth is a +3, we're taking that 6p3. We're not taking from the 5d or the 4f, right? We're going to take valence electrons first. If you have a negative anion, that means electrons are going to be added to the valence shell. So if it's negative, we remember this, electrons are added. If it's positive, that means electrons are taken away. So let's look at a couple of ions here. Let's say we had selenium -2. All right, so selenium -2, if I look at that really quick, 34 electrons in the atom. I've picked up 2, so now I have 36 electrons total. All right, and so I want to do the noble gas core abbreviated configuration for 36 electrons. And when I look at that, 36 electrons, that's going to match the noble gas structure of krypton. So rather than doing a noble gas core of argon and then doing 4s2, 3d10, 4p6, in this case, selenium, when it picks up 2 electrons, it actually matches that noble gas structure of krypton. So we're going to say that that is identical to the krypton structure. All right, if I have lead +2, all right, for lead, 82 electrons. If I've lost 2, that means I only have 80 electrons left. The core here would be the xenon core. And then after that, we would have our 6s2. Don't forget the 4f14, 5d10. And then what we think about is if it was a p +2, or sorry, lead +2, that means we've lost 2 electrons. So basically, instead of keeping that 6p2 for the atom, those electrons go away, and we end up at the 5d, or yeah, 5d. So we have the order of filling, sorry, we've got the xenon core, then we'd have our 6s2, 4f14, and then 5d10, and the 6p2 electrons here, those are the ones that have been lost. So we always remove the outermost electrons first, right? Last one here is the zinc +2. And so this one is where I think it's going to look a little bit strange. What I'm going to do underneath is look at the zinc atom first. So for the zinc atom, we have the argon core. And then after that, we would have the 4s2, 3d10. All right, so argon core, 4s2, 3d10. There's my zinc atom. Argon has 18 electrons, there's 20, there's 30. In the zinc +2 cation, remember you want to remove the outermost electrons first, the ones that are in the valence shell. So zinc now will only have 28 electrons in the cation, right? It's lost 2. But where do those 2 electrons come from? Remember when the D is filled, that acts like core, right? You always take from the highest occupied shell first. So it's the 4s2 electrons that go away. So what we're left with is that argon core, those electrons are untouchable. And then we'd have the 3d10. So we lost the 4s2, right? Those are the 2 electrons that have been lost. So that goes back to what we were talking about with the exceptions, why silver is always a +1. The fact that silver is always a +1 tells us that instead of it being a 5s2 4d9, it must be a 5s1 4d10, and that's why that 5s1 is always the +1 charge that's lost for silver. All right, so that's something a little bit new from intro, and again, I always found this to be pretty interesting, right? We We fill the 4s before the 3d, but then when we take away the 4s before the 3d, and that seems backwards, but that's the way this works. We always remove the electrons in the highest occupied shell first. Now the other new thing from intro is the two words, paramagnetic and diamagnetic. And I have to admit, this tripped me up the first time through, because what it's talking about is if the electrons are all paired, like we see in orbital diagrams, or if some of them are unpaired. And I remember, and don't do this, I remember thinking paramagnetic obviously means paired. No, it doesn't. You want to remember di for two. So diamagnetic means that everything is paired. So if all the electrons in an atom or ion are paired, this is diamagnetic. So just remember your di for everything coming in twos. If you have unpaired electrons, they're going to show an attraction to a magnetic field, and that's going to be called paramagnetic. So first, unpaired electrons in nickel. All right, so nickel, number 28, what we're looking at is we have an argon core. Then we would have the 4s2, and then we'd have 3d, and just finishing it out, 1, 2, 3, 4, 5, 6, 7, 8, 8 for nickel. All right, so how many unpaired electrons? What we know is that once the subshell is full, it means it's paired. So we really just have to look here, right? If we're looking at unpaired, we just have to focus on that 3d8. So for D, we need 5 different orbitals, degenerate orbitals. Again, the order of filling is we go up, 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 there's 5, and then down, 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 there's 8. So there's my D8 configuration for the nickel. And what this shows me here is that there are 2 unpaired electrons in a nickel atom, all right? And so again, what we would say here is that nickel is paramagnetic, all right? Because if it were diamagnetic, everything would be in twos, di for 2, right? So paramagnetic means we have unpaired electrons. So any unpaired electrons is where we have that paramagnetism. All right, on the next page, we've got a sulfide ion. So sulfide is a -2 charge, right? And if we look at that sulfur on our periodic table with 16 electrons in the atom, if it picks up 2, 1, 2, it's going to match the same configuration of argon. And what we know about noble gases is we have an S2p6, so that means all electrons are paired, right? So there won't be any unpaired electrons. And that means that this is diamagnetic. All right. An iron atom, all right, so iron Fe, number 26, has an argon core, 4s2, and 3d6. And so if I looked at that D, we'd have up, 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 and then D6 we pair down. So iron has 4 unpaired electrons. All right, and that would mean, and again, unpaired is not the same as valence, right? The valence electrons here would be the S2 and the D6. All of those are valence. Unpaired, when we're looking there, we're just looking at the orbital diagram and how many electrons don't have a pair, right? So that's unpaired. So again here, this would be paramagnetic, like we saw with the nickel. All right, now the cadmium ion, cadmium, I don't really use this one too much, but it is also a type 1 cation like zinc. It follows the same pattern. It's always a +2 charge. So what we would have here for cadmium is we had the krypton core, and then we would have had the 5s2 4d10, but we've lost the 5s2 because we lost 2 electrons here. And so what we know is that if it's a d10, right, that's full. So that means every electron will be paired. So there won't be any unpaired electrons, so no unpaired electrons. And so again, the term here would be diamagnetic. All right, so which of the above are paramagnetic and diamagnetic? If If your subshell is full, that means all electrons are paired. So that's diamagnetic. If your subshell is not full, there's going to be something that's not paired, right? So iron, and on the previous page, nickel, right? Those were paramagnetic. So just remember, di means everything is in twos, because that tripped me up the first time. The last part of the chapter are periodic trends. This is when we can look at just trends on the periodic table, just kind of qualitative information. There's 3, I think 4 actually, we do a new one. Atomic radius AR is basically looking at the radius of the atom, right? How big is the atom? Measures the distance from the nucleus to the outermost occupied shell. In the first part of this trend, we look at up and down and side to side. The first part of the trend makes complete sense, right? That is, we go down a family, radius increases because we're adding shells, so that makes total sense. So we know atomic radius increases as we go down the family. The side-to-side trend, I have to admit, that this one messed me up the first time through, because I thought atomic radius would be a direct link to the atomic number. So the more electrons, the bigger it would be, right? But that's actually not the case. When I look at, let's say, all the elements in the third shell, all right, so sodium, magnesium, 3s2, and then aluminum, argon, there's my 3p6, those in the 3p subshell. What you want to, and I don't want to tell you what I thought because that was wrong, so let me avoid that. What you think about here is for sodium to argon, all of their electrons are in the third shell. So if we go back to that atomic structure, right, we've got the nucleus in the center. Here's my first shell, here's my second shell, here's my third shell. So at first glance, you might even say, well, aren't those just all the same size, right? If I look at aluminum, it has 3 occupied shells, sodium, 3 occupied shells, argon, 3 occupied shells. So why wouldn't that just all be the same size? What happens, though, is that as we add positive charge to the nucleus, positive and negative attract. So as your positive charge increases, and we go sodium, magnesium, aluminum, and we keep adding protons to the nucleus, it brings in those electrons just a little bit more. That's supposed to be an arrow, right? So like a squiggly arrow. So it contracts the radius just a little bit. So it turns out that sodium is actually larger than chlorine. And again, that tripped me up because I was thinking it was going to be atomic number related. It's not. If we're in the same row, the elements on the left are bigger than the ones on the right, even though they have less electrons, because they also have less protons, right? Less protons in the nucleus to attract those outermost electrons. So the trend is atomic radius increases to the left. And I like any kind of mnemonic I can to help me remember things. So I always remember AR points to all the way left and down FR. So I remembered that trend. AR points to FR. All right, so if I'm comparing, for example, which one is larger, titanium or copper, I'm going to say titanium is larger because it's closer to francium. Or if I'm going to say which one's larger, iron or ruthenium, that one's easier because, again, that's more shells. That makes sense. Ruthenium's going to be bigger. All right, ionic radius. What we're doing here is we're just going to compare an atom and its cation or its anion, depending on if it's a metal or non-metal. So this one is much more intuitive, that if you lose electrons, you become smaller. And then if you gain electrons, if you gain electrons, you're going to become bigger. So this one to me was much more intuitive. So when I look at the sodium atom versus the sodium ion, we've lost electrons for the cation, so it's going to be smaller. And that makes sense, right? Because if I look at the sodium atom, it has 3 occupied shells. But for the cation, it's emptied that third shell and now only has 2 occupied shells, right? It has that neon structure. So when you lose electrons, right, the cation, this is always going to be smaller than the original atom, all right? So the atom is always larger than the cation. But we're comparing apples with apples, right? So it's got to be the same element. Likewise, when I look at adding an electron, because I'm not adding a proton at the same time, right? The nucleus is staying the same. The protons in the nucleus just can't bring in those electrons as well, so your radius gets bigger. So your atom of a nonmetal is always smaller in radius than the anion. The anion gets bigger. Okay, so first thing here, let's look at these sets of elements and arrange them in order of increasing atomic radius. So we're not looking at ions here, these are just atoms. If they were ions, they'd have to have a charge. But when you do ionic radius, you're only comparing it to the atom itself, not to a different atom, right? So just to the same element. These are all just looking at atoms. So we've got beryllium, fluorine, and nitrogen. So let's find them on our periodic table. We've got beryllium, we've got nitrogen, and fluorine. So when I look, right, the beryllium is furthest to the left. That one should be largest. And the fluorine is furthest to the right. That one should be the smallest. So if I'm going in order of increasing atomic radius, we expect fluorine to be the smallest, then nitrogen, then beryllium, right? Increasing as we go towards beryllium. Then next one we've got barium, beryllium, and calcium. This one's easier. This one doesn't trip up anybody, I don't think, because we've got beryllium and calcium and barium. Only 2 shells, 4 shells, and 6 shells. So it makes sense that the beryllium is going to be the smallest, calcium in the middle, and then I wrote beryllium, which is right. And I don't know if I said barium, and I'm double checking myself. So beryllium, only 2 occupied shells, that's the smallest of the 3. Calcium, 4 shells in the middle, and then the barium with 6 shells would be the largest. So increasing as we go down the family. Last one here, we've got chlorine, fluorine, and sulfur. So I've got my fluorine, chlorine, and sulfur. So certainly the smallest one would be fluorine because it only has 2 occupied shells rather than 3. So we can start there. Fluorine is going to be the smallest. And then when I look at chlorine or sulfur, whatever's closest to francium should be the largest. So chlorine we expect to be slightly smaller than the sulfur. So chlorine would be next, and then sulfur we expect to be the largest. All right, so that's the trend. Largest, we're starting with the smallest. All right, so that's atomic radius. Ionization energy, which is our second trend, this is defined as the energy required to remove an electron. All right, so that's the thing. We're removing an electron to make a cation. And these are all measured, and you can actually see them in tables. They'll list them as IE1 to remove the first electron, IE2 to remove the second electron, etc. And the first trend here kind of goes with what we learned in the beginning. Metals lose electrons pretty readily. Like the alkali metals and alkaline earth metals, they very much readily lose electrons. So their ionization energy must be pretty small. Like it must not take a lot of energy to remove an electron because they come off so easily. And then we know noble gases, you're going to have to try really hard to take away one of their electrons. So what we know about that first trend is that it definitely increases as we go across to the right. Now the family trend, like within a family, do we expect it to be easier to remove an electron from lithium or from cesium? And the difference is that with the lithium atom, the electron is pretty close to the nucleus. It's in the 2nd shell, whereas with cesium, it's in the 6th shell. That means there's a lot of what's called shielding. There's a lot of electrons in the way. The electrons in the 6th shell, remember that's not as happy for the electron as being in the 2nd shell. So it's going to be easier to take away a 6s electron than a 2s. So that ionization energy, or the energy required to remove an electron, definitely increases as you go up a family. So when you look at those 2 trends where we were, atomic radius is to the left and down, ionization energy is up and to the right. So it's the exact opposite trend. And if we want a mnemonic here to help us remember, if I look at my periodic table, up and all the way to the right is helium. So I always remembered IE points to HE, right? IE points to HE, just like AR points to FR. All right, so on the next page, we're going to put these elements in order of increasing ionization energy. So we've got beryllium, fluorine, and nitrogen. So same as what we were looking at earlier, beryllium, nitrogen, and fluorine. Beryllium, right, that's the only metal here, loses electrons pretty easily. Nitrogen and fluorine, nonmetals, they want to gain electrons. Fluorine is so close to neon, so close to having what everybody's looking for. So definitely doesn't want to lose. So in terms of the energy required to take away an electron, we expect beryllium to be the easiest, then followed by nitrogen, and then followed by fluorine. All right, and so if we compare that to what we did on the last example, it's the exact opposite, right? And that's what we saw. This trend is exactly the opposite. Then for the alkaline earth metals, barium, beryllium, and calcium. In barium, that electron is in the 6s shell, probably pretty easy to remove. Calcium in the middle, and then beryllium, the electron's fairly close to the nucleus in the second shell, so it's going to take more energy to remove it. And then the fluorine, phosphorus, and this time sulfur. All right, so we've got phosphorus, sulfur, fluorine here. If IE is the worst, that means fluorine should be the worst one here. Phosphorus should be the easiest, and then sulfur. Farthest away from helium, lowest ionization energy. Closest to helium, highest ionization energy. So phosphorus we expect to be the easiest, then sulfur, then fluorine. All right. Then the last two here, electron affinity, also measured as electronegativity. This is an attraction for electrons, right? How bad does that atom want to gain electrons? We know that that is higher for nonmetals than metals, right? The closer that outermost energy shell comes to being full, the more likely it wants to fill. And it's a measure of the energy change that happens when you add an electron, right? And at some point you get to that stability switch of the noble gas, right? So electronegativity, if we're looking at a desire to gain electrons, what's important to remember here is you're going to exclude noble gases from this, because noble gases don't want to gain an electron. They have the stability switch clicked on, right? But as we go across the periodic table to the right, that desire to gain an electron is going to increase. And also, the smaller the atom is, the better it will be at attracting an electron, because the electron can get closer to the nucleus. So if you compare that with the ionization energy trend, it looks exactly the same, up and to the right. The only thing that's different here is we can't have noble gases included in this trend. So if we go up and to the right but stop a column short, we have fluorine. And fluorine is our most electronegative element. That is something we're going to repeat a lot when we get into Lewis structures. So it looks just like ionization energy, just take out your noble gases. And the last one I think also is pretty easy to predict. It's called metallic character. So this one to me makes sense. We know that on the left side of the periodic table we have our metals, and on the right we have our nonmetals. So we have more metallic character on the left than we do on the right. So that makes sense, right? Fluorine is a nonmetal, no metallic character, right? Lithium is a metal, so we know metallic character must increase as we go back to the left. I maybe said right, but back to the left. So increasing as we go to the left. Now the up and down trend, this is actually easy to kind of visualize, let's say in the group 4, right? Carbon, nonmetal, silicon, germanium, metalloid, tin and lead, metal. So metallic character must increase as you go down. So this trend, what we know is metallic character increases as we go to the left and down. So to the left and down for metallic character. And if we go back to where we were when we did atomic radius, looks just like atomic radius. So basically you have 4 trends, 2 of them look one way and 2 of them look the other. So increasing to the left and down is metallic character. Increasing up and to the right is electron affinity and ionization energy. All right, that completes our notes for chapter 9.